Hence when we divide the filling area of each slot by the area of copper wire used or the conductor, we are able to determine the no of turns for that slot. Therefore, the cross-sectional area of the copper wire for main winding equals pi times radius equals pi times 0.4 times 0.4 equals 0.5 square millimeters, where the cross-sectional area of the copper wire for auxiliary winding equals pi times 0.28 times 0.28 equals 0.25 square millimeter. Hence we divide each cross section from the filling area of slot. We get for main winding, the num of turns per slot equals 26 square millimeters over 0.5 square millimeter equals 52 turns per slot. For auxiliary winding, the num of turns per slot equals 26 square millimeters over 0.25 square millimeter equals 104 turns per slot. So now we have up to now calculated mathematically the following characteristics gradually. Num of slots per winding, pitch of each pole, height of each winding, vertical, included the overhead width of each winding, horizontal, cross-sectional areas of winding wires, copper density of each slot and size of the fillable area, num of turns per slot for each winding, and a few more. Now we have come to an important destination, which is to calculate the resistance of each winding, since they are going to be loads to the electrical circuit of the motor. Thus, we are now able to determine the length of each winding as follows. For main winding, total copper length equals length of a single turn times num of turns times num of slots for both north and south poles. Hence it is equal to 415 times 52 times 8 equals 172.64 m equals 172 m. For auxiliary winding, total copper length equals length of a single turn times num of turns times num of slots for both north and south poles. Hence it is equal to 421 times 104 times 4 equals 175 m. The electrical resistance of a wire would be expected to be greater for a longer wire, less for a wire of larger cross-sectional area, and would be expected to depend upon the material out of which the wire is made. Experimentally, the dependence upon these properties is a straightforward one for a wide range of conditions, and the resistance of a wire can be expressed as follows. Hence now we know the total lengths of each winding and the cross-sectional areas. The resistivity can be obtained by the manufacturer of winding wires, and hence for the wires I'm using here, the resistivity is given as 1.72 times 10 minus 8. Therefore, if we calculate the resistance of each winding, we can end up with the following findings. For the main winding, A equals 0.5 square millimeters, L equals 172 m, hence R equals 5.9 ohms. For the auxiliary winding, A equals 0.25 square millimeters, L equals 175 m, hence R equals 12 ohms. Great. Now we have passed our first destination, and now I'm going to show you finding the remaining parameters. Before going to do the rest calculations towards power factor improvement, we have to sketch up the electrical circuit diagram of the single-phase induction motor. Hence, as I mentioned at the beginning of this session, this motor I'm going to design is to be configured as the PSC or permanent split capacitor starting method. Therefore, if I sketched you down, the circuit I have started designing is as follows, and herewith I'll bring back you the important parameters I have been determined up to now. 1. The resistance of the main winding equals 5.9 ohms. 2. The resistance of the auxiliary winding equals 12 ohms. 3. Expecting no load current equals 1.5 amps. 4. Power efficiency equals 90%. 5. Electrical power output equals 0.75 horsepower or 560 watts. 6. Supply voltage equals 230 volts, AC. 7. Frequency equals 50 Hz. 8. Expecting loaded current equals 4 amps.